here, I'll just cover up some our new progresses. Don't worry too much. We're not going to cover everything. We're going to go one by one some of these topics. But today, I really want to focus on the AD graph exploration. So we'll show more of these kind of sections. But let's start with the single-clonal human stem cell models. And this is the single-clonal. So when we first published 2014 our AD stem cell models, one of the technical limitations is they are very heterogeneous. And heterogeneous cell cultures, it has a lot of issues, especially it's not really consistent, reproducible, drug testing, genetic, a lot of problems. And even you cannot distribute as a cell models because every time you have it, there are changes. So this is it. And then also, taxi number, I can show you later, there's a huge problem with the taxi number discussion. And the most important thing is that this single clone, in our observation, it can accelerate pathological change. So when you have a mixed culture, it generally takes 6 weeks to get plaques and 12 weeks to get tangles. But in the case of single clone line, even you can get the plaques in 4 weeks, and 7 weeks is enough to get robust tangle pathology. And it seems like this is really not very important, but in terms of drug screening and other models, this is really big difference. And this is how it does. And I can skip these. And so this is a schematics of how we make a single clone line. So this is very similar to what you previously shown. That there are neural stem cells. We use Ranvian stem cell lines here, and then they are transfected with viral particles, which contains APP mutation, prison mutation, and then we do the text enrichment. And in the previous protocol, we just go to the directly 3D differentiation and drug treatment, and what we get is generally we got 6-week A-beta aggregation and 12 weeks half phosphorylation and aggregation. But what we did is that we added one more step, which is in here we do the FACS-assisted single cell clone, which is making everything in the single cell organisms. And this is one of the data we have. So we can see these 96 well, and these one is colonies generated from single cells. So these, we actually generate a lot of protocols to make this work. It's not that easy work, but we actually made it work. So these are the cells from single cells, and these are the validation. As you know, our cells are very robust, so we can just take out 10 microliter of media, and you can see A-beta in media very robust without using kits. And this is one of the examples. The single cell is really beneficial to get more homogeneous robust cells. This is one of cell line we published 2014 in Nature, and you can see that these green is APP and red is pristine. So cells generally do not like expressing pristine APP together. Why? Is because they are generating accidentally A-beta polymerase. So in the end, we got these mixtures, some of cells very high pristine, low APP or low high. And when it goes to single cell, you can see everything consistently expressed. And as a result of that, our most single clone line shows much more higher A-beta polymerase level and ratio. And the other really advantage here is that you can see here that these are really AD cell lines, very similar to total A-beta level. But you can see A-beta 42 levels are very different in this cell. So this cell line, like for example, A5 represents very early stage of Alzheimer's. But these cell line, H10 in the same condition, then they show robust aggregation of A-beta and tau pathways. So this is really great advantage to testing drug, because you can test drug in the different stage of Alzheimer's. Yeah. Okay, this is one of picture from there. So you can see there is a red is neurite, and then this is control cell. This is mild model, and then this is more stronger. But you can, I just want you to focus on the high stage lines, and then these green is A-beta aggregation, and these this blue is A-beta aggregation, and this green is just PFP. And this is MAP2, red is MAP2, and you can see this combination. So you can clearly see that these neural network, there are A-beta aggregation generated, And one more interesting thing is you can see these surrounding neurons, there are dystrophic neurons here. With all the dystrophic neurons around, you can see these are dystrophic neurons around there, and you can see those neurons are going around. And this is very similar to what we learned from Alzheimer's patient brain. So there are plaque generation, and generally we see very dystrophic neurons around the plaques. And we did the biochemistry, always confirmation after confirmation. This is another example. This is from the 3D gels. And you can see control, there's no A beta, but in the 7 weeks, just 7 weeks, and 80 cells. And there are different lines, but there are robust accumulation of A beta, not only monomers, dimers, trimers, tetramers, even hexamers. And this is SDS mutation aggregates is the sign that A beta is really aggregated into pathogenic forms. And this is EM studies, and you can see that I can just go directly here. We can appreciate these fundamental structures. And this is the particles, immunovoid particles, recognizing A beta specifically. So you can appreciate these aggregations. It's not like just the mix of all the A beta, but they are really making structures which you can see in Alzheimer's patient brains. And I can say that this is done within 6 weeks, and this is really accelerated in the single-clonal analysis to show much more robust thing. Let's go to the neurophysiologic tangles. It's a little bit complicated, but because Dr. Chu is here, I want to show this data. So in the case of tangles, I mentioned that it is important to have right isotopes of tau proteins. And in that case, these 4-repeat and 3-repeat tau is two very important players. This 4-repeat tau protein is isoform you can find in the other brains. And 3-repeat is only in the embryonic brain. And human brains, these are the 1-to-1 ratio. In mouse, there's nothing here, very strange. But problem we see is that in the older human iPS-derived neurons, we got really very small amount of 4-repeat tau. And 4-repeat tau is very essential for the tangles. They are really making aggregation. But in our current technology, we cannot make them with those more than 1%. That's the limitation. But really interesting thing is that with combination with 3D culture system and with our RAM-VM, the neural stem cells, we actually can achieve almost the same level as shown in human brains. We think that's why we have a success in the recapturing tau tangle pathway in this model. And we think this is something to do with the stage of neural stem cells we are using. Because the answer we used was from the 6-month-old human fetus. And this is generally late stages, and there are more capacity to go into the mature neurons. And we're still looking for some iPS-derived neurons that make these things possible, but we really having problems finding this type of patterns at this point. And this is a tangles, and how you can see neurophysiologic tangle. We have antibodies. These are the antibodies against pathogenic hyperphosphorylated tau species. And this is staining. You can see these are control cells, and these are really low magnification one now. And you can see these 80 cells have robust increase of this staining. And this is a high resolution, so you may appreciate a little bit, but you can see accumulation is in cell body and neurites. Resolution is not that great. Maybe I can go to these pictures. So this is a little better resolution, pseudo color. Again, this is pathogenic tau web. And you can see there are certain cells have those accumulated pathogenic tau. And here. And one thing also we found is that most of pathogenic tau accumulation leads to these dystrophic neurites. You can see neurites are unusual. So it actually seems like when the neurites have high levels of tau accumulation in the tangle, it seems like the neurites also degenerate at the same time. And this is not really surprising because that's what we think as a tangle pathway is connecting to neurodegeneration in Alzheimer's patients. And this is Western blot. So a little complicated, but here, again, this is another really big achievement in our view, because in our older cellular model, even mouse models, it's very hard to find these detergent insoluble. So these are the really Sarkozy detergent insoluble, very tightly aggregated forms. We can only see a lot in the human brain, but not even in the mouse model. But you can see here our model, and then you can see these top models have huge accumulation of these top protein solution, which really suggests that this really leads to aggregation of top protein in the fish models. And again, the resolution is not that great, but we can see that we analyzed with the EM, with the previous fractions. These detergent into the fraction was resolubilized and then undergoes to the EM, electron microscopy. And you can see these filament structures, and you can see not only filament structure, but you can see these twists between each helices. So as you know that tau tangles, the European tangle, there are several structures, but well-known structure is PHF, helical filaments. And that's actually signature of tau aggregation. And if you are looking at this, it's average of pitch size about 120 nanometers. And this is type you can only see it in Alzheimer's patient brains, not in the other tau path. So that's another confirm that this model recaptures closely those tau paths in other brains. And this is another immunostaining, but we can see these filament structures and these immunoparticles nicely show. Again, this is for the first time in the human model. Other models cannot recapture these strong aggregations. And the structure is not that easy to see because in these immunoglobulins, generally it destroys the structure even yet. It's not that easy to see. And this is EMRIs in the cell cultures, and this is AD cells. Again, we can see those filamentous aggregations only in the AD cells. So these all together suggest that our model within 7 to 8 weeks recaptured very advanced pathological status of Alzheimer's patient brain, at least for the A-beta plaque and tau tangles. And there's one more thing we noticed with the EM studies, because AD cells not only showing tau aggregation, but they look very sick. We see a lot of signature of mitochondrial deficit and others, and then we wonder whether that's the case. And answer is yes. So this is active caspase-3, those cell death markers, and you can see that especially with our cell line with high A-beta 42 levels, you can see there are robust increase of caspase-3. And you can also see the matrix staining in the control, and there are actually robust decrease of the derived network. And quantitation cells, there are really decrease the number of cell numbers in these AD cell line as compared to the control. And caspase activation also, as expected, is decreased significantly. One caveat is that this is interesting because when you look at more closely which cell express caspase and which cell shows cell death, and we found that majority of caspase, active caspase cells in here and here is non-neurons. Most of them is astrocytes. So idea we had before was generally we have tangles and neurons going down with the caspase-3 activation. That's a simple idea. It doesn't seem the case. So we are very interested in what's the role of astrocytes in these neuronal deaths.